So very often in the study of Markov chains, we want to know what is the mean time spent in transient states. So in my introductory video of Markov chains, I explained that a transient state are states that the system spends there temporarily, oscillating between various states until it enters an absorbing state, which is a permanent state. So once the system goes into this permanent state, it doesn't exit there, it just remains in that particular state. So if we talk about the mean time spent in transient states, we're actually talking about the average of how many steps the system remains in these temporary or transient states before being absorbed. So we can think of a few examples to contextualize this particular concept. So the first is that of the weather system. So let's just say we are in autumn, and the states we could define as being sunny, cloudy, rainy, and so on. And the system would oscillate between these various states before entering the absorbing state, which is that of winter. So in that case, the weather pattern would actually change. So if we talk about the mean time spent in transient states, what we're actually talking about is how many days the system remains active in sunny, cloudy, and rainy days before it actually goes to winter. So we're actually talking about how long this particular weather pattern lasts in autumn. So another example we can look at to illustrate this concept is that of the gambler's ruin. So I've done an entire video on the gambler's ruin in quite a lot of detail. But in any case, if we want to apply it to the mean time spent in transient states, well, we'll just look at what the states are to begin with. And we know that this is the fortune that a gambler has. So that's $0, $1, $2, and so on up until N dollars. So if you go back to my video on the gambler's ruin, you'd see that I explained that $0 and N dollars are actually the absorbing state. So either the gambler reaches the goal of N dollars or goes broke or ends up with nothing. So those are the absorbing states. So that's where the analysis of the Markov chain would actually end. So if we talk about the mean time spent in transient states, what we're actually asking is, what are the number of bets the gambler can place before he or she either goes broke or reaches the goal? So that's what we're talking about. So we'll start the analysis by looking at a specific example and then generalizing the result. So we have a Markov chain on the screen, and there's 3 states. So the system would bounce between states 1 and 2 because they are transient states, and then at some point it will reach state 3, which is actually the absorbing state. You can see that there are no arrows coming out of state 3 because if the system enters state 3, it basically stays in state 3. So let's write the transition matrix for this. So remember that when you're writing the transition matrix, the rows represent the current state and the columns represent the future state. So if we are in state 1, then the probability of remaining in state 1 is 0.5. If we're in state 1, the probability of transitioning to state 2 is 0.4, and then we can complete the rest of the matrix like that. From state 1 to state 3 is 0.1, state 2 to state 1, that's 0.3, then remaining in state 2 is 0.4, and then going to state 3 is 0.3, and then from state 3, you cannot actually go to states 1 and 2, and you can only remain in state 3, so it will put a 1 there. So this is our transition matrix. So in deriving the mean time spent in transient states, what we want to do is rewrite this matrix in a specific form. So the form that we want to write it in is as follows, where we have sub-matrices. So these sub-matrices are Q, R, 0, and I, where I is the identity matrix. So Q is actually the transition probabilities between the transient states. So in this case here, it's states 1 and 2. R is essentially the transitions from the transient states to the absorbing states. So basically the probability is from states 1 and 2 to 3. And then I is the identity for the absorbing states. So if we just look at this, we can see that Q is the transitions between 1 and 2. So they would correspond to the entries 1 and 2. That's row 1 and column 1 and row 2 and column 2. So Q is equal to 0.5, 0.4, 0.3, and 0.4. So this matrix Q is the one that we're going to be using to take forward in our analysis. So R is essentially equal to 0.3 and 0.1. So it's these two values, 0.1 and 0.3. And I is just equal to 1. Now let's talk about the number of steps that the system can go through before it actually reaches the absorbing state. So if we talk about the number of steps, what do we actually mean? Well, if the Markov chain starts off at state 1, then it can be in a number of places after one step. It can either remain in state 1 or it can go to state 2. If we talk about 2 steps, we're actually asking where is the Markov chain after 2 steps. So it can start at state 1, it can remain in state 1, and then it can remain in state 1 again. That would be 2 steps. Or it can remain in state 1 and then go to state 2 and then remain in state 2. So we want to consider the number of steps that the Markov chain goes through before it goes to the absorbing state. So that's actually the whole purpose of what we are trying to establish in this video. We are trying to establish what is the number of steps that the chain or the system spends in a certain transient state or visits a certain transient state before it actually ends up at the absorbing state. So we want to count the number of times it visits a certain state after a certain number of steps. We count those steps, and that number of steps, that average number of steps, is actually what we mean by the mean time spent in that particular state. So let's now take this transition matrix Q and write it for a certain number of steps and then add them up all together. So let's now look at 2 steps. So we'll take this probability matrix Q and we'll just write the entries as Q11. That's just the transition probability of remaining in state 1. Then we have Q12, then we have Q21, and then Q22. So when we talk about the number of steps, let's just say 2 steps. So in order for us to understand what happens after 2 steps, it means that this transition matrix will be there, and then the transition matrix will be there again. So we're talking about 1 step and another step. So we have to multiply this matrix by itself in order for us to understand what's happening after that certain number of steps. So let's just say 2 steps. So we're saying Q, and then we're saying it's squared. So that 2 means that it is after 2 steps. And how we compute this is that we take this transition matrix, that's Q12, Q21, Q22, and then we multiply it by itself. It's the first step, and then it's and the second step. So it has to be multiplication. So let's just multiply this out. We'll multiply the first row by the first column to get the first entry in the resulting matrix, which will be a 2 by 2 matrix. So we have Q11, that's 1, 1 times itself, and that's going to be squared. So then we're going to have plus Q12 times Q21. So it's Q12 times Q21. So that's the first entry in the first row. Then we'll have the first row times the second column. So it's going to be Q11 times Q12 plus Q12 times Q22. And then lastly, we'll have this second row times this first column. We're going to have Q21 times Q11, then plus Q22 times Q21, and row 2 times column 2, we're going to have Q21 times Q12 plus Q22 squared. So what do these entries actually mean? Well, what does this matrix Q squared even represent? It represents the current state that the system is in after 2 steps. So these entries, so the first entry, so when I say first entry, I mean row 1, column 1. What does row 1, column 1 mean of this matrix? So it's asking what is the probability of being in state 1 after 2 steps, given that you started in state 1. So that's what these matrix entries are. So if you look at row 1, column 2, so row 1, column 2 is actually showing the probability of being in state 2 after 2 steps, given that you started in state 1. So let's just write these indices. So you have row 1, row 2, we have column 1 and column 2. So as I was saying, if you look at entry row 1, column 2, it means that we are in state 2, or this is the probability of being in state 2 after 2 steps, given that we started in state 1. So let's just say we started in state 1, and then after 2 steps, we are in state 2. Well, there's several ways in which we can start off in state 1 and get to state 2. We could start in state 1, then we can go to state 1, or we could remain in state 1 and then go to state 2. Or we can start in state 1, go to state 2, and then remain in state 2. So let's show that. We can start in state 1, then go to state 1 after the first step, and then go to state 2. This is a tree diagram that I'm drawing here. So we can start in state 1, then go to state 2, and then remain in state 2. So this probability is Q11, and that is Q12, and that is Q12, and that is Q22. So the probability of being in state 1, remaining in state 1, and then going to state 2 would be that probability times that probability, because we have to multiply going down the chain like that. So it's going to be Q11 times Q12. And then we have to add up all the branches. We add up then the probability of going along that branch, 1 to 2 to 2. So it's going to be Q12 times Q22. So if you just remember what this matrix here represented, this Q squared, it was telling us what is the probability of being in a certain state after a certain number of steps, given that you started from a certain step. So Q squared 1, 2, right? So we would write this as Q squared 1, 2. So that is the probability of being in state 2 after 2 steps, given that we started in state 1, which is what we have drawn now in this tree diagram. And you can see that would correspond to this entry here, row 1, column 2. And if we compare that to our analysis, you can see it's the same thing. You can see that row 1, column 2 is the same as how we had gotten the answer from analyzing it using the tree diagram. So this is what this whole thing is saying. So now we have shown what is the probability of visiting a certain number of, or what is the probability of visiting a certain state after a certain number of steps. It's actually given to us by this matrix here. So if you wanted to see what is the probability of being in a certain state after 3 steps, then we would just do q to raise to the power 3, and then we'd have to multiply this matrix here now by this original matrix q. And that becomes a bit more computationally difficult. So now that we have the probability of the system being in a certain state after a certain number of steps, we can proceed to count it, and then that will tell us the number of times the entire process actually spends in that particular state. So we can now talk about N12, where N12 is the expected number of times the system or the process is in a particular state, in this case, state 2, if it starts in state 1 before eventually being absorbed. So this would equal to, well, firstly, the probability that it is in step 2, or rather, it is in state 2 at step 0. So when we talk about step 0, we're talking about right now. Remember that if we're counting the number of times that the process spends in a certain state, we have to consider the fact that it may have started in that particular state. So here we're saying specifically we're starting at state 1. So in this case, this particular probability would be 0. But then now, if this 1, and let's just say instead of 2, we had N11, if we started off at state 1, then it means that we have to count it 1 times before adding up this entire thing. So this would be 0 if these two numbers are different. So if this is I and this is j, so this is I and this is j, then this probability here, this first term would be 1 only if I is equal to j. So since I is not equal to j here, this first term would be 0 because we're saying specifically we're starting in state 1. Okay, so this is the first term. Then the second term is the probability that it is in state 2 after 1 step. So after 1 step. Then the third term is the probability that it is in state 2 after 2 steps. So this sum would go up to infinity. It would be the probability you're in state 2 after 3 steps, after 4 steps, after 5 steps, and so on. So these probabilities we have actually determined. So this first term is that identity matrix I. So if you remember I, for a 2 by 2 matrix, you got 1 and 1 and 0 and 0. So that's why I said you would only have a non-zero entry for I here if I is equal to j. In other words, we're talking about row 1, column 1, and row 2, column 2. So now this second term. So this probability that you're in state 2 after 2 steps, so that would be Q 1, 2. So that would just be the transition probability of moving from state 1 to state 2. Then after 2 steps, so this is literally what we have just shown now. So this is what it would correspond to. This matrix squared and the entry row 1, column 2. So it would be Q squared, where these are all matrices. And then we have 1, 2. So this identity matrix, I should also state that is entry 1, 2. So you can see 1, 2 is 0. So that's why it would be 0. Then the next term is this transition matrix Q cubed. And then again, entry 1, 2. And then this would go up to infinity. So now we can generalize this. So instead of starting from state 1 and then going to state 2, we can just say in general, starting at state I and then ending up at state j after a certain number of steps. And that would essentially be, we would change this 1, 2 to ij. So it would be ij plus qij plus q squared ij, and so on. So this refers to a certain entry. Now we can write it in general for the matrix N, which would have all of these entries of I and j and so on, so that n would equal to I plus q squared, and all of these are matrices. So this is an infinite sum, and you can see that it's quite analogous to another infinite sum. We're talking about the geometric series here. So we have 1 plus r squared plus r cubed. And this geometric sum actually converges if r is essentially a fraction. So if it's less than 1. So it is possible to show that we have a sum for this matrix in the same way. Firstly, this sum of this geometric series, you might remember from high school maths that this converges to 1 over 1 minus r, or 1 minus r to the minus 1. So in the same way that this geometric series converges to 1 minus r to the minus 1, it's possible to show that this sum of matrices actually converges to a certain matrix, and that matrix is I minus q to the minus 1, essentially the inverse. So if we have matrix I, which is identity matrix, and we subtract q, this probability transition matrix, and then we find the inverse of that, it will actually be what this matrix sum converges to. So this is the whole point of this exercise. This final equation tells us exactly what we want to know, because this n represents the number of times a certain state is visited. All of the states are basically encompassed in this particular matrix. So I'm not going to prove this here because it would take an entire video on its own. So let's just apply this formula now to this example that we have been looking at thus far. So if you look back earlier, you would see that q was equal to 0.5, 0.4, 0.3, and 0.4. And now we're going to compute this matrix n. So let's do I minus q. So this is just the identity matrix. So it's going to be 1 minus these entries along the diagonal, and then 0 minus the other entries. So that's going to give us 0.5, 0.6, and minus 0.4, and minus 0.3. So now we compute the inverse. And if you have a matrix with entries A, B, C, D, then you would recall to find the inverse of this, what you'd have to do is take 1 over the determinant of this matrix. The determinant here would be AD minus BC, and then we multiply it with some of these entries rearranged in this matrix. So we swap A and D. So you're going to have D there and A there, and then we change the sign of the remaining entries. So we have minus B and minus C. So we just apply this to this matrix that we have here. So we have I minus Q. We're finding the inverse of that. It's going to be 1 over 0.5 times 0.6 AD, 0.5, 0.6, and then minus BC, so it's minus 0.4, and minus 0.3. And we multiply this by this matrix. We're going to have 0.6, 0.5, those entries were swapped around, and then 0.4, and 0.3. And then we just multiply it. So I'm not going to do that each step. It's quite easy to do. And what we're left with is the matrix 3.33, 2.22, 1.67,
and 2.78. And this is the matrix N. So what does N represent? If we look at entry 1, that's row 1, column 1. So we're asking ourselves, if we want to determine what is the average number of times, steps that the matrix, the system would spend in a particular state, given that it started in state 1. So just to say that once more, let's look at row 1, column 2. Row 1, column 2. What is the average number of steps that the system would spend in state 2, given that it started in state 1, before it gets absorbed, or before it enters that third state in which it doesn't get out of? So let's just say we have 100 runs of this Markov chain. We run this chain 100 times. So let's just say we can start at state 1 or state 2. So let's just say state 1. So we start at state 1, and then we're going to end in state 3 because that's the final state, that's the absorbing state. So the question is, how many times, how many steps does the system spend in state 1 if it started at state 1? And that answer would be 333. So that means that it spends 333 steps in state 1 if it starts at state 1, if you run the chain 100 times. So for each run of the chain, it would spend on average 3.33 steps in state 1. This is an average. It's an expected value. It's not, there's no such thing as 0.33 steps. It's just the case that it means that if we have a large number of steps, like for example, a large number of runs, like 1,000 runs of the chain, then it means that it would spend 3,330 steps in state 1. It's essentially counting the number of times it would spend at state 1 if you run it 1,000 times, the chain. So in this video, the whole purpose was to determine what is the mean time spent in transient states, and the final outcome was the determination of this particular matrix. And we get this matrix N by actually counting the number of times or the number of steps the system or the process, the chain, would spend in a particular state, given that it started in a certain other state. And if we run the chain a certain number of times, then we can say on average how many times it would spend in that particular state. So thank you very much for watching.